Happy to be here today. My name is Brent Crenshaw. I'm with EPS. We make Forton. We produce acrylic latexes, and Forton is the product that we sell into the GRC market. I am from America. I'm sure you were all wondering, thought I was from London with my accent, but I am from America, and so I'll use GRC sometimes and GFRC sometimes, and just, you know what they are. Thanks to the people that organized, all the people that organized this. This is a fantastic conference, and I've loved it so far. I love being in London, and I'm excited to talk today. And I can figure out how to advance slides. Okay, so I'm a chemist by training and by temperament and personality and all the above. And little molecules, chemicals are little things. And there's a saying in English, I assume there's probably something similar in other languages, it's the little things. And if you look at it starts with it's the little things, and then it goes from there. So it's the little things that matter, that add up in the long run, that become big things, that get you caught, that make the difference. The little things sometimes piss me off. Little things count. Little things make you realize how good life can be. They give you away. They go a long way. They bring you joy. They become big problems. They make life big. They kill. They make a big splash. And today I want to talk about the little things that make a quality product and a good reputation. As Bob said yesterday, wherever he's at, talking about quality. It's the little things that add up into a really big 160-page PCI quality manual, right? It's a bunch of little things that go into production that make sure you have consistent quality product every time. Chemistry is all about the little things. The building blocks, like molecules or crystal structures that go together and they build kind of like Legos. You kind of snap them together to make structures, and from those structures come properties. So the structure of cement, depending on how that microstructure goes together, how much water's in there, how much cement, how much sand, how much polymer, it all adds up to give you a structure which gives you properties. And as a chemist, I love studying that structure-property relationship. I promise these are the only two molecules that I will have in the entire presentation. It's not a chemistry presentation from that standpoint. But the one on the left is methacrylate, and is methacrylate, and the one on the right is methylmethacrylate. The only difference is there's the CH3 group. I have a pointer. Is the CH3 group right here that is replacing this H. And that little difference makes a big difference in properties. In the same material, if you put one monomer in and instead of the other monomer, you can get a deck coating that lasts for 5 years on a deck, or one that completely peels off of a deck. You can get a coating for cement for hydrostatic water pressure resistance that works really well, or that produces bubbles in there. You can also have a piece of GRC that when you add Forton, you get something like this. When you add an SBR at a less than required amount, you can have something with a lot of cracks and yellow coloring. So it's just the little things that add up to be bigger things, quality products. So with that, here's my actual outline. Talk about kind of three things. Overarching, how does adding Forton to GRC work on the microscopic level to facilitate curing and retard aging? Forton is a cement admix, a polymer admix that is there to eliminate the need for a 7-day wet cure. So along with that, the chemistry behind why it's significantly more effective at these than dry polymer admixtures, and some testing results that talk about that. And then results, we started about 10 years ago, we started a study of naturally aged GRC panels and how the Forton modified ones compared to the ones modified without Forton. So concrete curing in pores. There are a lot of you out here that know a lot more about this than me, but this is just kind of my amazing artistic skills portrayed for you. it's enough to kind of show you to get the point across. When you put cement particles in water, they start to react with that water and they form the hydrated products. Those things grow and they really kind of start to meld and mesh into each other. But since you need more water in a system, as was mentioned yesterday, you've got to have, in order to spray concrete, you've got to have a little bit more water than is absolutely necessary to hydrate these things. So you're always going to have these extra little pockets that, called pores, or capillary pores, that water can flow through. This is just kind of an example where you've got, some of these pores are larger, some are smaller, and you've got these little kind of bottlenecks in there in various places that you've got to get through. When the larger these pores are and the more connected they are, the easier it is for water to get through the system, to move through the system. So when you demold GRC, it's typically after about a day. And that, at that point, those pores, cement, as you know, isn't completely hydrated yet. Those pores are still fairly large. At that point, it's very easy for water to move through these networks and evaporate. To keep that water in there, there's the 7-day requirement for a 7-day wet cure to make sure that there's constantly water around for cement to hydrate with. Shortly after alkali-resistant glass fiber came to be a thing, Forton was also added into the mix and was shown that it was enabled by adding 5% of that on by weight of cement. You could eliminate that need for the 7-day wet cure. How does that happen? It's kind of a somewhat complicated process, and honestly, we don't understand it perfectly. But in general, it works by keeping the water from escaping the system. I will come back to this. I put them out of order. So how it works. I've got the marvelous art there, display where water, you got the capillary pores and water in there. So first of all, you've got kind of two things that happen. As the cement cures, there's less space for the polymer in the water to be in, so it kind of pushes some of those out. And when the polymers come to the outside, the water evaporates, the polymer can't, and those polymers will coalesce, basically form a film on the entire outside of the surface. So you've essentially encapsulated the whole thing, the whole GRC panel piece with a semi-permeable membrane. In addition to that, you've got particles inside the matrix that get lodged. They're trapped in there and they get lodged in these capillary pores. They get lodged in the smaller places as water comes and evaporates out. You'll get, again, the water can get out, the polymer can't, and it gets stuck in there because of the MFFT, minimum film formation temperature, which basically means anything above that temperature, these particles can coalesce and form a film. Because of that property, they'll come together, they'll form a film, make this essentially a plug that slows down that retards the movement of the water. So water outside of there can evaporate, but it keeps most of the water inside, allowing it to hydrate. It doesn't do a perfect job because there's a lot of pores in concrete. But adding 5% lowers that diffusion and the ability for the water to leave enough to get it to keep the water in there well enough to give it the full wet cure. Now, see if I can go back. Yes. So, properties of a polymer curing aid. You've got two different specs. You got three different specs. Two different specs, though, with the GRCA spec and the PCI spec. Walk through this real quick, or maybe not real quick. Walk through this. Properties on the left-hand side, GRCA spec and PCI spec here. Aqueous, water, right? Thermoplastic polymer just means that when it's a polymer that when it's above that glass transition temperature can deform and form a film. Is what the thermoplastic polymer dispersion. Acrylic or acrylic copolymer based means that it's made up of those acrylate monomers. Those are, excuse me. Those are, acrylic is just, it's a polymer that's known to be resistant to UV light. resistant to hydrolysis, so it doesn't, when it's in the water in that alkaline environment, it won't degrade. Solids, 45 to 55%. The higher the solids, the more polymer you're getting instead of water or something else. Appearance, milky white, creamy, free from lumps. It's a quality assurance thing. If it's lumpy, then there's probably something you should call your supplier and talk to them about. UV alkaline resistance, good. We talked about MFFT already. Free monomer. That's basically lower the amount of residual chemicals in there. Odor, pH 8 to 10, close to the pH of cement. Average particle size, I'll talk more about this later, but the particle size, just keeping things consistent so you know, so it does the same thing every time. Particle size controls like the number of particles that are in there, and also the kind of the size of pores that can be blocked. Viscosity, again, it's just a spec, and freeze thaw stability is in there. We've got at least a dozen acrylic latexes that we make that meet all of these things on the PCI spec, these numbers there. It's impossible to specify everything that goes into a polymer curing aid without just specifying it's got to do its job. So that I said there's like a dozen of them that are in our portfolio that meet these specs, but most of them won't work in cement as a curing aid. Some of them will go into cement, but they won't work as a curing aid, and others just plain won't go into cement very well. So that testing is critical, and the long-term testing as well. Again, with quality, you can make a product and you can make it good enough to get your check. But ideally, you make it good enough to get your check, and it's going to last, and you're going to get repeat customers. You're going to get a quality reputation from the stuff that you've got out there. So that long-term testing is important as well. Okay, so we've been asked a number of times, well, why not dry polymer? Why does it have to be a latex? I've answered that question to a lot of people. I thought it would be a good thing to just talk about. There's three things that I kind of pull out to say why a latex instead of a dry polymer. Particle size is one. Oftentimes a dry polymer, the initial primary particle size is upwards of 400 nanometers. It's just a lot easier to produce a dry polymer that way with a larger particle size. Agglomeration, when you make these things, you make a latex, you spray it into the air, the water evaporates, and these things agglomerate into larger particles. Those are never 100% redispersible. Some of them get really close, disperse very well. Others don't disperse very well at all. But you never get 100% redispersion. So you start off with this many actual particles, and if they're in agglomerates, you just got a large chunk of a ball of polymer instead of individual pieces. And then the other one is 100% solids never equals 100% polymer. In the materials that we've checked, I've seen anywhere from about 50% polymer to about 90% polymer. And the remainder of that is either flow agents and surfactants. You need those to make sure that they can redisperse. And then there's fillers that are added in there to help with the flowing and whatnot in the system. So know what you're getting. We decided to do some testing. We got 2 dry admixes that were recommended for GFRC. We took Forton, and we had a control without polymer. And we decided to test these just in terms of matrix strength. We didn't want to test the ability of the glass fiber to disperse the strength and whatnot. We just wanted to test how well is the concrete cured, or is the mortar cured there. So experimental design, we used a water to cement ratio of 0.32, sand to cement of 1:1, polymer to cement. Forton, we put it at 5%. That's what we recommend. Dry admix 1, the max recommended dosage is off, but they both had a maximum recommended dosage. So we put in what they labeled as their max. So we put in 4% of one, 6% of the other as they directed, and then we had a control using no polymer. We added super plasticizers as needed for flow. Cast coupons 2 inches by 12 inches by ½ inch, covered with plastic overnight, demolded in the morning, and cured in air the rest of the time, except for the no polymer control was cured with the 7-day wet cure. At the end of the 7 days, we tested the flexural strength using the 3rd-point bend test. You can see the results there. We've got the flexural strength and generally correlating to the LOP of the materials on the left. On the right here, yeah, you're right. You've got the displacement or the flexural strain at break. You can see the control down there, the dry polymers on the right, Forton on the left. In general, the dry polymers did have some effect. They did increase compared to both the flexibility and the mortar strength compared to the control. At the same with all the other parameters the same. But the Forton was much more effective. 130% improvement in strength, 200% improvement in flexibility compared to the control, whereas the dry polymers are about 70% and 100% improvement in flexibility. So there's definitely a difference. Again, if you're going to use something that Forton's been used since basically the beginning, close to the beginning of GFRC. If you're going to use a different polymer, test it, so you know what you've got. Just a commentary on particle size. Said the smaller the particle size is, the more individual particles you have, the more and smaller holes you can plug, etc. Just to kind of conceptualize that, if you take a square, a cube of material, give it a characteristic length, call it D, as 1, goes across the whole thing, and the number of particles there is 1. If you cut that in half in all 3 directions, 3 axes, D equals a half, you have the number of particles becomes 8. If you do the same thing again, it becomes 64. And in general, the number of particles is proportional to 1 over the diameter cubed. So if you want to compare, if you have particle size of a resin, primary particle size of the resin, and you want to compare 2 different resins, you can essentially divide the diameters cubed, and that's the difference between the 2 of them. So if you have a 400 nanometer particle and a 150 nanometer particle, you've got 19 times more particles with a 150 nanometer particle than you do with a 400 nanometer particle. So the difference in particle size isn't that big, but the difference in number of particles and how well that's dispersed, how many particles you have throughout they're dispersed, is significantly different. More is not always better, but in this case, more particles equates to more and smaller pores plugged, better distribution, and a smaller particle will give a faster, more effective cure, film formation in this system. So in the end, know what you're getting, test. Switching topics. How am I doing on time? I have no idea. 2 minutes left? That's not right. Okay. You all know how GRC ages. It embrittles, calcium hydroxide will dissolve in water, and then as the water evaporates, it's going to deposit again, or it's just going to, it dissolves and it moves and it builds crystals. Those crystals are in the, oftentimes get into that, the empty space in there, the fiber bundles. And they clog up the fiber bundles, making it so that you get the GFRC goes from a very ductile material to a very brittle material. How do polymers work in there? Just like when the cement is curing, or while it's curing, you've got water that's evaporating. There's a lot of space that those small latex particles can get into. When the water evaporates, the polymer particles can't, and they will build up in these fiber bundles. I mean, the bundles are essentially giant superhighways for water, and anything smaller than that, it can travel through there very quickly, but the polymer will get in there and it will bind in there. Again, what that does is control the movement of water. The slower the water goes in and out of the system and around, the less the calcium hydroxide is going to dissolve and build up in other spaces. To look at this, 10 years ago we started a project looking at GRC made with the same water to cement ratios, using Forton and using no Forton. And 2 years ago we showed the results up to 24 months. We've got 10 years results in here now. you can see the Flexural Yield, we're growing, both of them grow. The Flexural Yield increases a little bit, with Forton a little bit more than without. The Flexural Ultimate, with Forton it's actually going up, whereas without Forton it's going down. And the Flexural Yield, you can see basically with Forton it maintains a lot of its original ductility. After 10 years, you've got 85% of the ductility remaining when you're using the 5% Forton, and only about 33% of that of the initial value when you don't use Forton. My time is up. That's what I wanted to present to you today. So thank you. Here's my conclusions. But the one I really want to hit on is high quality GRC leads to good materials, good reputation, and market success overall. So thank you.